Hello Internet, what is going on? My name is Arenda, and so a little while ago I was browsing some nice Reddit forums, and I came across a couple of posts talking about sort of why is the sine wave the fundamental tone of music, and so what are the differences between how that sounds and a saw wave or a violin or a guitar. And so for me, I just didn't feel like enough of the math was covered to really get a full picture of it. So what I want to do right now is create a video that gives maybe a more comprehensive look at sort of what exactly is sound from a mathematical standpoint, and sort of how can you take that and carry it over into getting a better understanding of your DAW or your music production or your instrument of choice. So what this is going to do is sort of start from the beginning and sort of give a pretty in-depth look into the ideas behind what is a tone, what is a fundamental frequency, what are the harmonics, and how do we get there from the physics themselves. Alright, so I wanted to do a quick little humble brag segment just to give you an idea of why I feel I'm sort of qualified to talk about some of this. So I'm a producer, that's my dream job, or where I hope to get to at some point. But I'm also a massive nerd, and I'm a senior in engineering at NC State, and I've had engineering internships with Rolls-Royce Aerospace and Native Instruments, as in the music company based out of Berlin. So because of that, I feel like I've got a pretty good perspective on sort of how to talk through this stuff, and I've actually been through all the math in an academic setting that I'm going to be discussing here today. So let's get into, to start off, what exactly is a wave, and this can be in any context. This is a wave of light, a wave of sound, or a wave in the water. And sort of what a wave is on the most basic level is energy that's getting transferred through a medium. So if I plug the string here on my guitar that I'm conveniently holding, what you can hear is actually the energy transfer of the vibration of the string, of the energy from when I displaced it initially or plucked it, and that energy is then getting transferred via waves through the air into my ears, or in this case to the microphone, and then to your ears. But so there's a little bit more to it than that. So there's a quantum version of this. You may have heard of the Schrödinger wave equation. But fortunately, for physical things, there's no probabilities or quantum mechanics. There's a Newtonian form of this, which you can see written at the bottom of the screen. Now this c squared here is, in this case, the speed of sound. For light, that would be the speed of light, and of course the speed of sound is different for water or for air. It's a property of the material through which you're transferring energy. So there's actually a different speed of sound in the guitar string than there is for air, and those actually are important properties when you're trying to derive the equations for things like this, because they'll give you different numbers. So let's talk about the most simple way to create a wave, and that would be with a mass attached to a spring. Now, if you've had a Physics 1 class, you've probably done this experiment before. So if I've got a mass, or a ball or something, and I hang it off of a spring, and I pull it down and let it go, it's going to bounce back and forth. And you can sort of see the conclusion at the bottom of the screen here of where we're getting, that the motion in time is going to be in the shape of a wave. But let's talk about a little bit as far as what each of those pieces of a mass spring system are, and how they behave in a mathematical context. So the mass of the system follows Newton's second law, which is to say that if I apply a force with it, it's going to accelerate at a rate proportional to its mass. Force equals mass times acceleration. Most people know that, F equals ma. Now, for our purposes here, we need to make one other very important edit to this, which is that acceleration is the second derivative of position with respect to time. And this allows us to formulate this equation with respect to the position of the mass itself. So we get to say that force is equal to mass times the second derivative of whatever this equation x is that governs its position in space. So if I've got a go-kart or something, and I floor it, the x of t is going to be its position, x prime of t is going to be its velocity, and x double prime is going to be acceleration. So that is a very important concept here, and this notation is what we're going to be using for the rest of the video because it's a lot more convenient than trying to write out dx dt or d squared x dt squared every single time. This is very common in physics. So now the last component of this system is a spring, which we assume for this purpose to be massless, or that the mass is included within the mass term and not within the spring term. So, excuse me, a spring is going to obey what we call Hooke's law, and that's force is equal to kx. And all this means is that if you push on a spring, if I've got a spring and I compress it together, the spring's going to push back in the opposite direction of how I displaced it. And if I push it more, it's going to push back harder. That's really all this is saying. And k is just a constant that describes the relationship between how hard I push it and how hard it pushes back. Alright, so that's that. But now we've successfully defined the two terms, and really those are the two fundamental equations that we're going to need. For those of you who know a little bit more about this, I'm going to ignore damping for this video. Combining the two, how does a system move? So, what this equation here is saying is that the spring, if I displace a mass from a spring and let it go, the spring is going to generate a force. Now that force is equal to kx from Hooke's law. And then that force is going to create a mass times acceleration because F equals ma. Now this negative sign here comes because the acceleration is inversely proportional to the direction of the spring. So if I pull the spring down, it's going to accelerate up. If I push the spring up, it's going to accelerate down, and vice versa. So that's where this negative sign comes in. Now, rearranging that, we get this thing which conveniently equals 0, and the second derivative of this x of t term, which is x double prime of t, has to be equal to some proportion, which is going to be k over m, times negative x of t. So what that is saying is these two have to have opposite signs, and there's got to be some proportion relating them. Now, let's get into the math a little bit. So there are two functions that have the second derivative of themselves equal to the inverse of themselves. And that's a bit of a mouthful, but the reality is what comes out is that your answers are sine and cosine. And obviously the sine is called the sine wave, and you can see that at the bottom. It's got a wave motion. So really the reason why the sine wave is considered a pure tone in music is because it's the simplest solution to this one-dimensional equation of a mass and a spring moving together. And that is the simplest way to generate a wave, and it is the simplest solution to a wave problem. And so because of that, it creates a pure tone when you do this fast enough that the motion actually goes into the audible frequencies. You can prove this, and this whole second derivative of x of t has to be proportional to negative x of t. You get that by using Calc 2 Taylor series expansions. And I thought the math for that was a little bit too long to put into this video, but if you want to prove it, you can look that up on Wikipedia, which is actually a great resource for these kind of things. But just know that you can prove that the easiest and only equation actually that satisfies this is a sine wave or a cosine wave, which is actually just a sine wave offset by a phase angle. Now what's cool is you can actually see this. If you've ever had a slinky and you've pulled it down and released it, you've seen the lower end go up and down in a sinusoidal motion. Now a pendulum behaves like a sinusoid, except it's moving in polar coordinates, so it's moving around a point as opposed to moving in a vertical or horizontal axis. But so you can see that this does in fact work, and it's going to form the basis for everything else that follows after it. So now let's get to air. So air has mass, obviously. So that's the first thing we need to get out of the way. But now there's one more property of air that we've got to observe, and I'm going to prove it using a bottle rocket. So I've got this empty bottle of water here, and if I compress it by twisting it, the air is applying a force back, and that force gets released when I shoot off a bottle rocket. So you can see that air clearly has some sort of spring property. So air is a mass spring system. So we've got a mass, we've got a spring. What does that mean? That means that it behaves in a manner that it will move in waves. So this entire idea of a fluid that's compressible and also has mass means it can behave like a wave. And what you see here is that air and sound behaves like a longitudinal wave, where you've got these series of compression and expansion that transfer sound, or in this case energy, gets transferred to your ear by energy that's moving in waves. So now we've established a good definition for sound. Now we're actually going to tie these two concepts together, because we have this thing that we've invented called a speaker. Now what's really cool about a speaker with relation to what we've just talked to is that it's exactly a mass spring system. The spring is the cone of the speaker, and the mass is the magnet at the center of the speaker. Now, what is actually happening to generate your music is you've got an electromagnet inside the speaker, and that electromagnet is generating a signal. And that signal comes from your MP3 file that's been amplified through an amplification circuit, blah, blah, blah. But what's actually happening is the electromagnet is turning on and off and changing its frequency to make the speaker move. And the speaker is then vibrating as a mass spring system, which makes the air vibrate, which gets transferred to your ears. So you can see that we have a direct mass spring system, but also that the air is following as a second mass spring system to get the sound out of your iPod or your speakers or your DAW and into your ear. So yeah, we've got physical waves out of electrical waves via the speaker system. And again, touching back onto the idea of air as a mass spring system, what's really important about it is that it's continuous, and that's going to change its behavior a little bit, and we'll see what the effects of that are here in a minute. So now we're going to get to something that's really important for the idea of especially music production, I think. This idea has helped me so much in understanding exactly what's going on when I'm looking at graphs of sound and of music that I've been writing. So we're going to look at what a harmonic is and why it works. So if you have a string on a guitar, I've got my guitar here for demo purposes, it's going to behave as a mass spring system. Now, if I pick any point on this guitar and look at the string, it's going to be vibrating up and down, and that motion is going to be roughly sinusoidal because there's not too much that's interfering with it. But now let's say I wanted to create some sort of plot of the entire motion of the string at once. Now, how would I find solutions for that? So what we're going to look at here is the idea that there are multiple solutions to that problem, and it depends on what are called the initial conditions. Now, if I just pluck the string normally, the vibration amplitude is going to be the highest at the middle of the string, and it's going to be 0 at the ends of the string. They're fixed. But let's say I specify a different set of initial conditions, and we've still got to satisfy the wave equation. We've got two parts. We've got an x dimension and we've got a time dimension. The x dimension is the length of the string, and the time dimension is time. But now we want to prescribe the motion given these two variables. So Different frequencies can satisfy this equation, but it depends on what you do to the string initially. So, to prove that, I'm going to put my finger on the 12th fret and let it go. And what you've got is a different tone, a different frequency. And that's as a result of the fact that the wave equation can have multiple solutions that all work depending on the initial conditions. Now, there are a bunch of these too. And if you have a guitar, you've probably done this. And you probably know that these are called harmonics. Well, this, if I just pluck it, is the fundamental. But if I change the conditions so that at the beginning, the middle point is fixed, then I get a different solution to the same wave equation. And you'll notice that this motion is stable even after I take my hand away from it, meaning I don't have to keep my finger there for this solution to be valid. Alright, so now let's get to probably the most complicated part of this, which is superposition, or this idea that multiple waves can hold the same space at the same time and not interfere with each other. Now, this is a very sort of difficult thing to grasp, but if I pluck the string and I lightly put my finger on the 12th fret, where we've already said that harmonic was, you can actually hear both tones at once. So if I pluck that and then put a little bit of harmonic on it, both of those tones are superimposed on top of each other. And so what we have here is that this is the equation that governs how the string moves and what frequencies will work. It's a function of the speed of sound of the string and the length of the string, as well as some other properties that are called initial conditions. But to solve for this frequency, you get a number of different solutions. So you've got this one, which is the fundamental frequency, or the lowest possible frequency that works as a solution to the system. That's going to be the first harmonic, that's going to be the second, third, and so on, all the way down. And all of these solutions work, and as I've sort of shown here, by putting my finger lightly on the 12th fret, they can all sort of coexist with each other. And so the math term for this is that each of these motions is called a mode shape. And it's sort of this abstract concept that means the shape at which the string moves. So if I put my finger here, essentially these are vibrating up and down inversely from each other. That's one mode shape. If I put my finger there, you get a second mode shape, etc., etc. But all of these different mode shapes can sort of coexist and exist in different proportions on top of one another. These solutions are mathematically what's known as orthogonal, which means that I cannot take some amplitude, I can't pluck this string hard enough that it will give me that solution. All of these solutions are known as linearly independent from each other, which means that they can all exist at the same time and be completely fine. This is sort of like how if you've got two light waves that pass through each other, they interfere at specific points, but they both can pass through each other equally. The same idea applies to the transfer of energy through the string. And that's because of orthogonality. So I'm just going to include a note here that the math for this fucking sucks, and I hate it, and it's not fun, but I honestly have gotten through some of the classes because I've sort of had this physical model of I've been able to look at my guitar and see, oh look, these harmonics really exist. I can understand that and I can prove that more so than trying to do it on paper. Alright, so now that we've established that all of these solutions can exist on the same string or in the same air or on the same speaker, they can all exist at once. Now, if I've got wave motion in 2D, it can be some linear combination of these different frequencies and mode shapes. So it's got this fundamental, it's got the first harmonic, it's got the second harmonic, it's got the third harmonic, and so on. But they can all exist together and in different sizes, so different quantities, which we're going to call constants here. What those actually are the individual amplitudes of each harmonic. So 1 times omega, which is our fundamental frequency, is the fundamental frequency. Everything else, you can call it either an overtone or a harmonic. They both of those terms work. But this is why a guitar sounds different from a violin, because when I pluck it, it's got a set of conditions that creates a different number of overtones than a violin, and those overtones have different properties that create the unique sonic texture of a guitar. Now the same goes for saw waves or square waves or anything within a DAW. Now what you can see here is the fact that as you draw more and more of the harmonics onto this graph at different frequencies, the limit of the sum of those waves approaches a square wave, which is to say that the square wave is made out of a bunch of tiny little sine waves that are all various harmonics of the fundamental frequency, which you can see here in red. So it works for the guitar, it works for sine waves, which are just the fundamental, and then it works for square waves and saw waves and everything else you can make within your DAW. So this is, like I was saying, what creates the differences in sound between instruments. It's also important to note that you've got an additional modifier that creates another set of conditions if you've got the body of the guitar, which creates a different set of resonances because you've got this resonating chamber. And that works because we've already talked about air also follows this wave equation. And so this guitar body is specifying another set of conditions that change the sound. And so if I had a violin body, that set of equations would be a bit different, etc., etc. Alright, so now this is actually getting into the math that your DAW does to display an EQ. So we've already talked about that waves are composed of a fundamental frequency and a number of harmonics that can all exist together in peace and they're all happy and shit. So we care about frequency and we care about amplitude. So these are the constants that I've just sort of assigned. How can we display this? So we've already talked about that our function of time, which is our wave, is made up of some frequency times some amplitude plus another frequency that's the harmonic times the harmonic, etc., etc. But how do we take this and make it something that we can display or we can process or we can interpret? So it turns out there's something called the Fourier transform. And this transform I have a rather unhealthy attachment to be honest. I love it a little too much. So the Fourier transform essentially takes this and converts it into a set of coordinates that tell you information about your waveform. And it takes this function in time and converts it to a function in frequency, which is from the time domain to the frequency domain. And they're called domains in math, but really all it means is this wave is vibrating in time, but it's going to take it out of the idea of time and put it into the idea of how fast is it vibrating, and also how much vibration is it? Is it a little vibration or is it a lot of vibration? So the Fourier transform is going to take one sine of 1t, or our fundamental frequency, and it's going to map it to a set of two coordinates, one for the frequency and this one for the amplitude. So your y-axis is how much of the signal there is at that point, and the x direction is what frequency you're at. Now, if you've ever looked at one of your EQs, you'll know it starts at around 25 and goes up to like 20k hertz. And what that is actually displaying is the Fourier transform of your signal itself. So I've got that picture down here just as an example. So this graph right here is actually a graph of the individual sine waveforms that make up this signal as a whole. So how does the computer do it quickly? Well, there's an approximation called the fast Fourier transform. And what this does is a whole bunch of simplifications to make it really, really easy for your computer to do this at the expense of frequencies that are outside of the audible range. So it essentially lets your computer perform this calculation very, very quickly a number of times. So your EQ is graphically displaying the result of that transform. And this is a really important concept, not just if you're using an EQ on a DAW, but if you're just playing an instrument and where are these overtones coming from? Well, if I pluck a guitar string and record that into Ableton or whatever DAW you use, and then look at the EQ, that's going to show me what frequencies are being played when I pluck the string. Now I can go in with the EQ and shape it to take out different frequencies or whatever I happen to want in my sound. But that's actually the mathematical underpinning of what's going on there. So if you look at a saw and a square wave, especially one that you play in like the C0 octave, you'll notice that they have different harmonics. And again, this is just another observable thing to show you that this is actually happening. So the fundamental and the harmonics, the human ear mainly hears sort of the fundamental motion of the signal, but then the harmonics are what gives your sound its character. So I'm just going to go back through most of what I've said a little bit. So a wave is really just energy transfer. So it's taking the energy from this guitar string and bringing it to my ear. The guitar string is taking the energy from my thumb and putting it into the motion of a string. The simplest equation that follows a wave is a mass spring system. So if I hang a ball from a spring and displace it, it moves in a sine wave. So that system's motion, that's the most simple mass spring system that behaves like an energy transfer system, gets motion prescribed by a sine wave, and you can use some math from Calc 2 to figure out why the sine is the answer to that equation. Continuous systems, like strings, can have a bunch of solutions called harmonics that are determined by the initial conditions of the system, which is these two ends of the string and where my finger is at the start of the string. And each of these solutions is individually a sine wave, but they can all exist happily at the same time. Air behaves like a mass spring system, and this is really important for understanding why sound gets from the string to our ear. Because the string is a mass spring system, it's vibrating, the air is also vibrating, and it follows the same equations as the string or even the ball that we bounced up and down. The exact motion of the string can be specified by the initial conditions, which again gives us the harmonics that we can actually hear really easily. And so because the sine wave is the simplest solution to a mass spring system, we're going to say that the Fourier transform takes that as a base unit or a fundamental frequency and transforms everything else based on the harmonics of that signal to basically be able to graphically display all this information in a frequency map. So the fast Fourier transform lets your computer do this really fast, and I think that's sort of the last thing I got. All right, thank you guys for watching. So I'm going to put some of my links up here for my music and for my Twitter that's utterly degenerate, and I highly don't recommend it. Yeah, if you want more music, you can go ahead and subscribe to this channel. You gotta smash that like button. Oh. Yeah. Why did I put this in the video? Why did I put this in the video? Oh God. Yeah. Thanks for watching.